Find the non-trivial solution of the Sturm Liouville problem d square y upon dx square plus lambda equals to 0, equation 1, y 0 equals to 0 and y pi equals to 0, equation 2. Now solution. We shall consider separately the three cases: lambda equals to 0, lambda is less than 0 and lambda is greater than 0. In each case, we shall first find the general solution of the differential equation 1 and then attempt to determine the arbitrary constants in these general solutions, so that the supplementary conditions 2 will also be satisfied. The case 1, lambda equals to 0. In this case, 1 reduces to d square y upon dx square equals to 0, or d square y equals to 0, where d is equal to d over dx. The auxiliary equations d square equals to 0, that is d equals to 0, 0. So its general solution is y equals to c1 plus c2x. We now apply the condition 2 to the solution 3. Now condition y equals to 0 implies 0 equals to c1 plus c2 into 0, or c1 equals to 0. Thus the condition y pi equals to 0 implies that 0 equals to c1 plus c2 pi, or c2 equals to 0 since c1 is 0. Thus, in order that the solution 3 to satisfy the condition 2, we must have c1 equals to c2 equals to 0, but then the solution of 3 becomes yx equals to 0 for all values of x. Thus, in the case when the parameter lambda equals to 0, the only solution of the given problem is the trivial solution. Case 2, lambda is less than 0. The differential equation 1 is d square y upon dx square plus lambda y equals to 0. Its auxiliary equation d square plus lambda equals to 0, where d is equal to d over dx, which implies d equals to plus minus square root of minus lambda. These roots are real and unequal. Since we have lambda is less than 0, let us denote the square root of minus lambda by alpha, and we have the general solution y equals to c1 e raised to power alpha x plus c2 e raised to power minus alpha x, equation 4. Now we apply the boundary conditions 2 to the equation 4. The condition y 0 equals to 0 implies c1 plus c2 equals to 0, equation 5. Now condition y pi equals to 0 implies c1 into e raised to power alpha pi plus c2 e raised to power minus alpha pi equals to 0, equation 6. Now clearly c1 equals to c2 equals to 0 is a solution of 5, but these values of c1 and c2 would not give the non-trivial solution of the given problem. Now we must therefore seek the non-zero value of c1 and c2, which satisfy 5 and 6. This system has non-zero solutions only if the determinant of the coefficients is 0. Therefore, we must have determinant of 1, 1 and e raised to power alpha pi and e raised to power minus alpha pi equals to 0, or e raised to power minus alpha pi minus e raised to power alpha pi equals to 0, or e raised to power minus alpha pi equals to e raised to power alpha pi, or e raised to power 2 alpha pi equals to 0. This implies that alpha equals to 0. Now since alpha equals to minus square root of lambda, we must then have lambda equals to 0, but lambda is less than 0 in this case. Thus there are non-trivial solutions of the given problem in this case of lambda is less than 0. Now case 3, lambda is greater than 0. In this case the auxiliary equation of d square plus lambda equals to 0. So its roots are d equals to plus minus square root of minus lambda. Now these roots are conjugate complex numbers. Since lambda is greater than 0, so the roots can be written as plus minus square root of lambda iota. Thus in this case the general solution is of the form of y equals to c1 sine square root lambda x plus c2 cos square root lambda x, equation 7. Now we apply the condition 2 to the general solution. Condition y0 equals to 0 implies c1 sine 0 plus c2 cos 0 equals to 0, which implies c2 equals to 0. Condition y pi equals to 0 implies c1 sine square root lambda pi plus c2 cos square root lambda pi equals to 0. Since c2 is 0, so c1 and square root sine square root lambda pi equals to 0, equation 8. We must therefore satisfy the 8. So we can either set c1 equals to 0 since sine square root lambda pi equals to 0. However, if c1 equals to 0, then since c2 equals to 0 also, the solution of 7 reduces to the trivial solution. Thus we obtain the non-trivial solution. We can set c1 equals to 0, but rather we must set sine square root lambda pi equals to 0. Now n is greater than 0 since n pi equals to 0 only if n is a positive integer, n equals to 1, 2, 3 and so on. Thus in order that the differential equation 1 have a non-trivial solution of the form of 7 satisfying the condition 2, so we must have lambda equals to n square where n equals to 1, 2, 3 and so on, equation 10. In other words, the parameter of lambda of the 1 must be a number of the infinite sequence 1, 4, 9, 16 so on, n square and so on. Thus we have seen that the lambda is less than equal to of 0 is the Sturm Liouville's problem consisting of 1 and 2 does not have a non-trivial solution. If lambda is greater than 0, a non-trivial solution can also exist only if lambda is one of the values of given by equation 10. Also from 7 we see that non-trivial solution corresponding to lambda equals to n square, n equals to 1, 2 and so on are given by y equals to cn sin nx where n equals to 1, 2 and so on, where cn is a arbitrary non-zero constant.